So I'm going into these details at the moment. So some of the features, I'm not doing an exhaustive listing, but these are the basic features that are being implemented. So we do 1D to 3D. We can go to higher dimension, and there is no restriction there. Basically, the geometry is order, or dimension is a parameter. Simplices, tensor product, hexahedron, hypercubes, other types of convexes. We support various point sets, so either for quadratures or interpolation, and in particular, we are interested in developing high-order methods on simplices. So we have various types of point sets which were developed in the recent years, like the FEniCS warblend or electrostatic, in order to come up with the difficulties of building high-order Lagrange polynomials. I mean, if you build them at equispaced point sets, then you will get a very bad Lebesgue constant, right? When you increase polynomial order. Then, of course, there are various kinds of polynomial sets that are supported, like Lagrange, Dubinaire, boundary adapted version, Legendre, and boundary adapted version, and other kind of finite elements. And support continuous and discontinuous Galerkin methods. All the parallel framework basically is built on PET-C and Trilinos. So basically, there is a very light layer on top of PET-C and Trilinos, and then you can choose, depending on the feature you would like to use, you can choose either PET-C or Trilinos. I'm not using all features of both frameworks, but basically the linear and non-linear frameworks are being used in both cases, and also as you can see, SLEP-C here is a layer on top of PET-C for eigenvalue problems. And basically we have tools, mainly localization tools in 1D, 2D, and 3D. So the language is embedded in C++, is very close to FreeFEM. I used to be at the beginning. I used to be a developer at the beginning of FreeFEM. So I was in the team who developed FreeFEM. Now it's called FreeFEM++, and I think this is a very important tool for the applied math community. And I decided to build a language which was very close to this one. So the concepts are in your code with life. You have to manipulate basically 4 types of concepts. Basically the mesh, which is built on top of convexes, basis functions, approximation spaces, which are parameterized by the mesh, and basis functions, and then forms and operators, and eventually associated containers if it applies. The form and operators are basically the glue between the linear algebra and the function space and rational formulation. Okay, I talk about this is just another example. Well, this is still Navier-Stokes, but just another example here where we would like to have an equal order approximation for Navier-Stokes, so PN typically, and this is a type of term that you would need to add in order to ensure that you have that you deal with the spurious modes typically, right, in order to have to satisfy the discrete IM subcondition properly. So here is the architecture of the library. Nothing really particular, except that, well, we try to be numerical type independent, to be able to parameterize what we can do with respect to numerical types, that is being able to support how would I say, higher order precision, double, quad double, complex and or automatic differentiation numerical types. Here I have the core. So I have to say that life builds on top of many libraries of Boost. I think this is a very important C++ library, and I use, whenever I can, I reuse the Boost libraries. I use many of them. I will talk about that a little bit later. I talked already about the linear algebra, which builds on top of PETC and trilino. Then I have the layer, the polynomial set layer, which has various kind of tools like functional sets, being able to evaluate, differentiate, integrate. Then you have the geometric transformation, finite, spectral, and HP elements, integration methods. Yeah, wow. So the point is that in the end, we would like to write application, be them mono or multiphysics, mono or multiscales, and we would like to have the language here is a very important piece because it allows to hide all the technical details which are written below, and so you manipulate only the concepts or abstraction that are required for your problem here, and you don't want basically to manipulate low-level details that are here. So the language which is at this level allows to hide all the details that are or many of the details that are here, actually. So regarding the polynomials and polynomial sets, it builds on top of work by Robert Kirby and his Fiat library, and also on the work of Sherwin and Kariadakis. So basically, what we have is the way we treat it is basically algebraic treatment or representation of our polynomials. We express our polynomials in an L2 orthonormal basis. So on simplices, that would be the Dubiner basis, and on quadrangles or hexahedron on Legendre basis. It provides some nice features, like it's very easy to extract bases which span a subspace of a particular space. You have exact integration that could be useful, and it's easy to construct. I think it's very easy to construct polynomial families. Yeah, and so we have support for scalar, vectorial, and matricial polynomial and polynomial sets. So here is non-exhaustive list, and here this is basically you have to parameterize that with respect to the polynomial order. Yep. For example, one very nice thing, just a comment about, for example, Lagrange, is it's like 20 lines of code, but it's for a very wide, the code, the 20 lines, they encompass a very wide range of views, right? So it's like continuous Galerkin, discontinuous Galerkin, high order, simplicity, 1D, 2D, 3D, simplices, or hypercubes. It's exactly the same code, right? And if you look, for example, at line 5, then in this respect, it's a catastrophe because you would have a special case for each type of Lagrange polynomials. So here, with this way of building the polynomial set, we have a very, very short library. And I think since we are very few developers, it allows to, by exploiting the genericity of the construction, we manage to keep the library very small. I think it's very small. But I think it's very important in this respect, because otherwise we just build a very big code and it's very difficult to manage it.
Are these reference elements? Are you using the reference element?
Reference element.